Hello and welcome to today's video on the history of sets in mathematics. Sets are a fundamental concept in mathematics, and their history dates back several centuries. In this video, we will explore the origins of set theory, its development over time, and the contributions of various mathematicians to its evolution. Origins of set theory. The concept of sets can be traced back to ancient civilizations, such as the Babylonians and Egyptians, who used sets to organize and count objects. However, it was not until the 19th century that the foundations of modern set theory were laid. In 1874, German mathematician Georg Cantor published a paper in which he introduced the concept of sets and their properties. He also proposed a new branch of mathematics called set theory, which aimed to formalize the concept of infinity. Development of set theory. Cantor's work on set theory led to the development of several important concepts, such as the concept of cardinality, which measures the size of a set. He also introduced the idea of transfinite numbers, which are numbers greater than any finite number. In the early 20th century, mathematicians such as Bertrand Russell and Ernst Zermelo further developed set theory by introducing axioms and formal systems for reasoning about sets. Russell's paradox, which showed that the naive set theory proposed by Cantor led to a contradiction, led to the development of more rigorous axiomatic set theory. Contributions of mathematicians. Several mathematicians have made significant contributions to the development of set theory. In addition to Cantor, notable figures include Richard Dedekind, who introduced the concept of a cut in the real number system, and Abraham Fraenkel, who developed the Zermelo-Fraenkel axioms for set theory. Other notable mathematicians who made contributions to set theory include Kurt Gödel, who proved the incompleteness theorems that showed the limitations of formal systems, and Paul Cohen, who introduced the concept of forcing, which is used to prove the independence of certain mathematical statements from set theory. Conclusion. In conclusion, the history of sets in mathematics is a long and rich one, spanning several centuries and involving many important mathematicians. The concept of sets has evolved significantly over time, and it continues to be an important area of research in mathematics and other fields. By understanding the history of sets, we can better appreciate the significance and complexity of this fundamental concept. A set is a collection of distinct objects or elements. These objects can be anything, such as numbers, letters, colors, or even people. In this video, we will discuss all types of sets, give examples of each type, and explore their applications in daily life. Type 1. Finite sets. A finite set is a set that contains a specific number of elements. For example, the set 1, 2, 3, 4, 5 is a finite set because it contains 5 elements. Another example of a finite set is the set of colors in a rainbow, which consists of the 7 colors red, orange, yellow, green, blue, indigo, and violet. Finite sets have numerous applications in daily life, such as in counting the number of objects in a collection, determining the number of students in a class, or counting the number of items in a grocery bag. Type 2. Infinite sets. An infinite set is a set that contains an infinite number of elements. For example, the set of natural numbers 1, 2, 3, 4 is an infinite set because it contains an infinite number of elements. Another example of an infinite set is the set of real numbers, which contains all the numbers between negative infinity and positive infinity. Infinite sets are used extensively in mathematical fields such as calculus and analysis. They are also used in real-life applications such as measuring distances or time intervals. Type 3. Subsets. A subset is a set that contains only elements that belong to another set. For example, the set 2, 4 is a subset of the set 1, 2, 3, 4, 5, because both 2 and 4 belong to the original set. In other words, all the elements of a subset are also elements of the original set. For example, if we have a set A equals 1, 2, 3, 4, and another set B equals 2, 4, we can say that B is a subset of A, because all the elements in B, 2 and 4, are also in A. Now that we understand what a subset is, let's explore the different types of subsets. Type 3. Proper subset. A proper subset is a subset that contains some, but not all, of the elements of the original set. In other words, A proper subset is a subset that is not equal to the original set. For example, if we have a set A equals 1, 2, 3, 4, and another set B equals 2, 4, we can say that B is a proper subset of A because it contains some elements of A, but not all of them. Example: if we have a set C equals 1, 3, we can say that C is a proper subset of A because it contains some elements of A, but not all of them. Type 4. Equal subset. An equal subset is a subset that contains all the elements of the original set. In other words, an equal subset is a subset that is equal to the original set. For example, if we have a set A equals 1, 2, 3, 4, and another set B equals 1, 2, 3, 4, we can say that B is an equal subset of A because it contains all the elements of A. Example: if we have a set D equals 1, 2, 3, 4, we can say that D is an equal subset of A because it contains all the elements of A. Type 5. Singleton subset. A singleton subset is a subset that contains only one element of the original set. For example, if we have a set A equals 1, 2, 3, 4, and another set B equals 2, we can say that B is a singleton subset of A because it contains only one element of A. Example: if we have a set E equals 3, we can say that E is a singleton subset of A because it contains only one element of A. Type 6. Empty subset. An empty subset is a subset that does not contain any elements of the original set. For example, if we have a set A equals 1, 2, 3, 4, and another set B equals, we can say that B is an empty subset of A because it does not contain any elements of A. Example: if we have a set F equals, we can say that F is an empty subset of A because it does not contain any elements of A. Subsets are used in various fields, such as in computer science for organizing and searching data, in genetics for studying gene variations, and in finance for analyzing investment portfolios. Type 7. Disjoint sets. Two sets are disjoint if they have no common elements. For example, the sets 1, 2, 3, and 4, 5, 6 are disjoint because they do not share any elements. Disjoint sets are used in set theory to study the relationships between sets. They are also used in real-life applications such as in surveys, where disjoint sets can represent mutually exclusive choices. Type 8. Union and intersection. The union of two sets is the set of all elements that belong to either of the two sets. For example, the union of the sets 1, 2, 3, and 3, 4, 5 is the set 1, 2, 3, 4, 5. The intersection of two sets is the set of all elements that belong to both of the two sets. For example, the intersection of the sets 1, 2, 3, and 3, 4, 5 is the set 3. The concepts of union and intersection are used in various fields such as in databases for querying data, in probability theory for calculating probabilities of events, and in linguistics for analyzing language structures. Type 9. Universal and empty sets. The universal set is the set of all possible elements in a given context. For example, the universal set for a survey of favorite ice cream flavors could be all the possible ice cream flavors. The empty set, also known as the null set, is the set with no elements. For example, the set of all prime numbers could be considered an empty set since